India rank 1 in UPSC Engineering Services examination.
Hello friends, welcome to this session of important concept discussion for data structure. And I am going to take you through this session. My name is Abhishek Sharma and I welcome all of you to this ACE Engineering online platform where we will, in the next 1 hour, we'll discuss some important concept related with data structure. So agenda what I have thought of that there is few concept I can explain you from the different topics, and here the first thing that I am going to discuss here is the construction of a tree by using order which is post order and pre order. So you might be familiar with the construction of post order and in order, and you might be also familiar with pre-order and in order, but here I will take you through this a special case where in some cases you can use post-order and pre-order for the construction of a tree, and in one case special case I will show you where using only single traversal, using only single traversal, pre-order or post-order, you can construct your tree. Okay, so that is the first concept that I will going to explain here in this cases. The second is I'll take one problem, as I said earlier in the yesterday's session, that the entire data structure, the perspective should be the complexity and the understanding of the operation, the cost of the operation, that must be also very clear to you while reading only the data structure. Not only the representation in the memory and how this works, but cost of the operation is also important. So I'll just take one question with that particular background, which is a complexity background. So this is one question I will take from this linear data structure, which is a linked list. Then I will focus on the next part, again a tree concept here in this cases, which is AVL insertion. Okay, so AVL tree, basically I want to focus here the cost of construction cost. Okay, the construction cost of AVL tree. Okay, construction cost means time complexity. Construction cost here in this case is the time complexity. Time complexity of binary search tree, and in this case is AVL, so balanced binary search tree, balanced BST. So this I will focus here for the next question, balanced BST. And the last year I will say take the concept of heap counting, that how can we count the number of heaps, and I'll present this heap counting through an example which is in question form. So all the concept I am going to say in question answer format here in this cases. So let us continue here, and here the first is, as I said, that one of the concept that I am going to discuss, that I can get my tree using post order and pre order, but not in all cases. It is not, you might have heard this term that we cannot, one of the traversal should be your in order. One of the traversal should be in order, but you can, in some cases, you can construct the tree by using only pre-order and post-order, and that special case is when the given tree is a two-array tree. Okay, if the given tree is a two-array tree, then you can make this tree, the construction of the tree, you can do two-array tree by using post-order and pre-order. What is a two-array tree? So a two-array tree is a tree. Okay, a two-array tree is a tree in which each node is having each node is having 0 or 2 children. Each node is having 0 or 2 children. Each node is having 0 children or 2 children. 0 or 2 children. Okay, so each node is having 0 or 2 children. That is the two-array tree in this case. So if the internal, like here, this is means differently written, but that is also to at least has at least 2 children, then tree can be determined in a pre-order and post-order traversal here in this case. Each internal node is having at least 2 children, then we can get this this pre-order and post-order traversal. How? So I'll just explain this thing, then I'll show this the same thing by using an important in animation form. So I will show you that animation. Now we know that the pre-order traversal, the traversal sequence is root, left and right. Okay, and here in this the root here will be, in this case, will be definitely A, and this is also suggesting that root will be in this case is A. So A is the root of the tree. For a two-array tree, I am talking about this situation. Two-array tree, I am talking about this situation. So here A is the root of the tree, and here in this you can see that now this tree is having either 0 children or 2 children. Two-array tree I am talking about. Please ignore this one line, that is another case actually. So there that I will talk about later. But here I'll explain you the two-array tree part. So here A is the root of the tree, and this is having either no children or there will be 2 children. Because it's an internal node, there will be either no children or there will be 2 children. But now I can see here that in this we have number of nodes are there, and that means the root here in this case is having both left and right children. Only one children, that situation will not occur for, let's say, let me stress this, a two-array tree. So left of A will be, in this case, is after root you visit the left children. So left children will be, in this case, will be B. Because it's non-empty, there are nodes here, left and right, both nodes are there. So after visiting A, you are going to visit the left children, which in this case is pre-order traversal root, then you go to the left. So the B will be on the left here in this case. So B is on the left. Then for what is the post traversal? So left, root and right. Okay, left, root and right. So this is, I'll write here in this, left, root and then right. Sorry, left, right and root. Sorry, left, right and root. What is pre-order? Root, then left, then right. So this is the sequence of visiting the nodes. So after root you are going to visit, B is on this left. Before root, the node that you are going to visit will be the node or the last node, which is the, basically in this case is, that is E. So after root you are going to visit the node or the subtree, for left subtree the root, which is B, and before the root you are going to visit the root of the right subtree. So this is the first thing by which I can draw this, that after A, left root of the left subtree, and before A, root of the right subtree will be visited. So in this case, this will become here in this case is E for sure. Okay, E. So root, left and right. Now what is the more, now here I know here in this case is that after root, left and right will be visited, and E is the root of the left subtree. Now I'll come back here in this case is that E and this, and now I use this information to divide my sequence. And if you look at and divide, if you look at the sequence here, again I'll go to the A is now sorted, B is the root of the left subtree because the left subtree will be again visited in same order, root, left and right. So B is the root of it, and observe one thing here in this case is that if there is a right subtree will also follow the same sequence, root, then left and right. That means if there is any children of E, and there must be 2 children, at least 2, internal node, okay, leaf node we are not saying, internal node, if you have at least 2 children, in that case, after E, right subtree, it will, after E you are going to visit left and right children. But look at your pre-order traversal, after E you are not visiting any node here. This is the only route, and after that left and right should be visited, but here in this case there is no left and right. Okay, there is no left and right part. And hence I can say that E is the only node on the right subtree. This is the first conclusion that I will draw, and with that I can say that this is the structure, that is what is the division here in this case. How I concluded E is the leaf node. I concluded E as a leaf node because my sequence of right subtree will be same, root, then left, and then right. But here only E is there. After that, what is left? Empty. What is right? Empty. Okay. So now I can now divide that what is the what is the limit of the left subtree, to up to G, and after E it will be start the right subtree. So this is the for A root, this all element B, C, D, F, G is on the left subtree, and only E is on the right subtree. Fine. This will generate, give me another sequence B, C, D, F, G. Okay, I'll write that sequence for you. B, C, D, F, G, and here this is pre-order sequence. And what is the post-order sequence here in this case? The post-order sequence is C, F, G, C, F, G, D, B, D, and then B. So C, F, G, D, B, that is the sequence here in this cases. Which one is the root? So first node is the root, B is the root. Which one is the root? Post order, B is the root, so B is the root here. Again this same thing will be divided into left and right subtree. And I know that after root I go to in the pre-order traversal left, so C is on the left because more number of nodes are there, C is on the left, and D is on the right. Okay, and here in this case is this sequence is okay, B, C, D, F, G. So here C is on the left and D is on the right, because before B the next node is visited here in this case is D. So this is my construction of with this result that I can go here in this case is D. So this is your D. Now again the same conclusion, that which one is it, both are having the left and right, both are having the division. I want to divide this entire part, who is on the left, who is on the right here in this cases. Now observe the same thing here, observe the same thing, that after B you are going to visit the C. Then in pre-order, if C is the root, then after C you are going to visit the left and right childrens of it. Okay, root, then left and the right. If C is the root, the next you should visit is the childrens of C. But in pre-order traversal, after B you come to C, then directly you are going to the visit D. And the conclusion here in this case is that after C, directly if you are visiting in this case is D, then what? Then the simple conclusion that we can that is here in this case is that C does not have any children. C is the leaf node. Again repeating that after root you are going to visit the childrens of C, which is left and right. But here in this, after C directly I am going to visit D here in this cases. So now with this pre-order traversal, I can again say that in this pre-order traversal, because you are visiting after C directly you are visiting to D, that means in this situation C is the leaf node. So now my division of this will become this, and based on this I can also divide this over here in this. Another conclusion that I can show here, that C is a leaf node. Look at the post-order traversal. Post-order traversal, what is the sequence first? You must have a very deep understanding to understand this particular part of this post-order and pre-order sequence. Because if that is not clear, I cannot extend that concept. What is the post-order? You visit the left, you visit the right, and then you visit the root. Left, right, and then root. That means before visiting the root, you will complete the left subtree and the right subtree. In post order traversal, directly you are going to visit C in this cases. Okay, directly you are going to visit in this cases C. And before C is what? Before root there should be left and right, but before C nothing is there. And if before C nothing is there, that conclude only one thing, there is no left and right children of C, and C is the root node. So both the way you can conclude that after C, the one hint is that you are directly going into D. How I come to know C and D is the children? Because after root you visit left, so after B left is C, and the condition, the special case is that they are having either 0 children or 2 children, at least 2. So in one way that at least 2 thing that I said is basically another way of saying that 0 or 2, at least 2 means greater than equal to 2. So here after C, in this case B, you are visiting C, that is on the left. Before B you are visiting D, that is right. After C directly D, that means C is a leaf node. Before C nothing is there, that also concludes C is a leaf node. So C is a leaf node in this case. So now once I know the division, I will carry forward one more time this pre-order and post-order traversal, and I'll write here the pre-order here in this way, that pre-order traversal is D, F and G. So D, F and G, and F, D, G, post-order traversal in this case is post-order traversal is F, D, F, G and D, F, G and D. What they are suggesting, who is the root? Pre-order, first one is the root, the D is the root. Yes, I have drawn the D as a root in this cases. Post-order is also suggesting that D is the root. Yes, I have drawn that also in this cases. Now, if you look at what is the left child, so after root you are going to left, which is in this case is F. So F is on the left. It's an internal node, that means there will be both node will be present. Left and right both will be present. That is the special case. Okay, structure wise. If that structure is not given to you, it is not possible because multiple traversals are possible. Multiple trees are possible for same traversal. Multiple trees are possible for the same post order and pre-order traversal. But for the special case, there is a at least 2 children or 0 or 2 children. Okay, greater than equal to 2 for internal node. Leaf node 0, it can be okay. But internal node 0 or 2 children. D. What is the right child of D? So before in post order I will get here in this case is the right child, which in this case is G. So look at here, I am able to successfully construct this tree, and this tree is a special tree, as I said that this condition is applicable for only 2-array tree. This is the same situation, at least 2 children means internal node. Here I missed in first part that, but here internal node, yes internal node, this is B is internal 2 children, A is internal 2 children and D is internal M. So another way of saying 2-array tree is the definition in this case. That is the construction process, a special case where we can use the pre-order and post-order traversal for construction of this tree, special case. Let me demonstrate the same situation here, special case that A is the root, as I said that A is the root, that is it is suggesting. And here in this A is the root and before E, okay, E is the children, that is right child, so E will come on the right. Why? Because in post order left, root and then right. So before root there will be a children which is be the root of the right subtree E. Similarly, this B will become from the pre-order traversal, that this will become here in this case is the right child. So that is your B. Again B is the root. What is on the left? So B, C will be on the left, okay, and D will be on the right. So this D is on the right. And what is on the left here? So what was the argument? The argument is this, and how can I conclude that only C is on the right? That after C, the first is that you are going to visit the D. After C, you are directly going to visit D, And in this situation, before C, nothing is visited. So before C, if nothing is visited, left and right, nothing is there, then only you are coming to C as the root. That means C is on this left child. With that, I can go forward with D, F, G and F, G, D. What is the root? D is the root. What is on the left? F. What is on the right? That is G. Okay, so G is on the right and F is on the left. That is the tree construction, a special case by using pre-order and post-order traversal. That was the first concept that I have discussed. And what are the property that I am using? A special case. Remember, do not apply everywhere. Do not apply this thing everywhere, because this is only applicable when your given tree is a two-array tree. That is the only situation it is applicable. It is a two-array tree. Okay, that is a two-array tree in this cases. Now, first concept. Okay, that is the first concept for the day. I'll extend this concept to another special case, and this special case, this question is true or false. The question says that another concept, same traversal. If we are given only with the pre-order traversal, only pre-order traversal is given to you, only single traversal, only one traversal, that is a pre-order traversal. What is pre-order? Root, left and right. So I don't know who is on the left, who is on, I don't know anything about this. I have no idea that who is on the left, who is on the right. Correct? Only pre-order traversal of a full binary tree. This is full binary tree. So let's first, again, structure has been defined in this. What is the structure? So structure here is the for full binary tree is every level is full. Some book mention this full binary tree as perfect binary tree. So perfect binary tree. And perfect binary tree, the structure will look like this. This is the structure of a perfect binary, structure only. This is a perfect binary tree with 3 nodes. This is a perfect binary tree or full binary tree here with 7 nodes. And this is the perfect binary tree with 15 nodes. Perfect binary tree. What is the property? That structure will look like this only. This is the structure of a perfect binary tree. In this perfect binary tree, one more thing is there, that height, the number of nodes in perfect or full binary tree. In full binary tree of height h, okay, this is another concept, full binary tree of height h. Binary tree of height h, height, what is height? Height defined from the root is at height 0. This is your height 1. This is your height 2. And this last value in this case is height 3. So the number of node at height h in a perfect binary tree or full binary tree is 2 to the power h plus 1 minus 1, always. Formula for perfect binary tree. 2 to the power h plus 1 minus 1. H is what? Height. So what is the height here in this case is 3. So here the 2 to the power h plus 1, 3 plus 1 minus 1, and that is equal to, here in this case is 2 to the power of 4 minus 1, and that is equal to 15. So this tree must consist of 15 nodes. This is a 15 nodes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. This formula is applicable for high touch. Another concept you can say. This is another concept. But the idea is that every level will be full. This is a compact representation with n node. Compact means there is no single space left in this representation. 2 to the power h plus 1 minus 1. So this we are talking about. So here the number of node is fixed and moreover structure is also fixed. So here a full binary tree is given to you, and here we know that this is having 7 node. You can count it, 7 nodes are there. That means I know the structure. I know the structure here in this case, that this full binary tree is having this structure. Believe me that once I know the structure of the tree, I can label this, I can fill this node, the value, by using this pre-order traversal. Is it a pre-order? Yes, it's a pre-order. Only traversal I can do the filling of this. How? So now I know that this is a full binary tree and A is the root. You cannot deny this fact that root left and right. So A is the root. Root, left, and then right. So A is the root here in this. A is the root here. And with this structure I know that 3 node on the left, 3 node on the right. So now I can use this information for this division, that there is a 3 node on the left and there is a 3 node on the right. So BEF is on the left and CHG is on the right. But again, this is a subtree, left subtree, and it will also have a root. Who will be the root? B will be the root. And it is also saying that this structure is also saying that B is having a root and it is having a left and right child also. So what is my sequence? Root, left and right. Root, left. So if B is the root, E will be on the left and F will be on the right. Similarly, C is the root. G is on the left and H is on the right. So look at here, I have not used any other traversal. Only one traversal. And I fill up the entry in this cases. Obvious question can be here in this that may come in your mind, that is it possible, this rule is also possible for in order, pre-order, in order and post order? Answer is yes, it is also possible when the traversal is post order and in order. It is possible. If you recall the process of construction of the tree by using traversal, which is pre-order and in order, or post order and in order, you use in sequence to define the left and right, because why in order helps us, because in order exactly divide the entire array into the left, root and right. That is the sequence for in order. So I know that A is in the middle and the left part is the left subtree node and right part is right. That information we apply onto the post order or pre-order, because that gives us the information about the root. But in this case, the structure is fixed, and hence with only one traversal I can reconstruct this tree. Only one traversal. Similarly, if you give me post order or pre-order, then also I can construct the tree for this. That is the second concept, and this statement is what? True. That only one traversal can I construct the tree. Answer is yes, you can construct it. Next. repetition. This is a pre-order traversal for a full binary tree. This one, next. True or false, another concept for the traversal. You may say that why we are discussing tree. So yesterday I told you in last session, the tree is important. Tree is important. All types of tree. And one of the major portion in tree, 18% of the question of PYQs are from tree. And among them, further you want to divide into the subtopic, all the different subtopic, you will find that the maximum number of questions from the tree belongs to the traversal part. They are simple in nature, and definitely you should not lose that marks, because everybody more or less remember this or understand this simple concept of the traversal of binary tree. Next, if we are given only post-order traversal, single post-order traversal of a CBT, complete binary tree, CBT, then we can always construct that binary tree uniquely from the post-order. Then means again here that only one traversal, but this time it is a CBT, complete binary tree. So let's understand first what is a CBT. CBT structure, complete binary tree structure. So basically application of CBT complete binary tree. Now you can answer it, all of you, that application of complete binary tree and why we need this tree is in which data structure, which data structure is having a CBT, complete binary tree. The data structure which is uses this complete binary tree we use for heap, binary heap, max and min heap. So what is a CBT? CBT is a structure where every level is full. Now here then you say what about full binary tree? Full binary tree is also every level full. So every level is full. What is a CBT? Complete binary tree, every level is full. So for complete binary tree, every level is full. Let me complete the statement. Every level or height, every level is full except possibly the last. Except possibly the last. And in last level, and in the last level, elements are arranged from left to right. Left to right. This is the definition of a CBT. That means here what is the structure with the 7 nodes? So now I have some space here less, so I'll just draw here. So now here this is a CBT, yes, and here last level may be full, may not be full. So this is also a CBT, complete binary tree. May not be full, doesn't matter. Then if I add a node, what about this? Yes, it's a CBT. Last level may not be full. So this structure is a complete binary tree, CBT, complete binary tree. What is not a CBT? This is not a CBT, complete binary tree. And if I put a node here in this case, this is not a CBT. In this, the right child of this particular node, this is not present here. this is not present in these cases. The right child of this node is not present and you start filling. So every level is full, element will be arranged left to right. So that second property violated here. So I know the structure again in this case is that if the total number of node is 6, what I also know in this case here is the structure, that this is the structure. 3 node, 6 nodes are there. So this is your 4, this is your 5 and this is your 6. So CBT is structure, like full binary tree was giving us the structure. CBT structure is also a fixed structure. CBT structure is also a fixed structure. Post order traversal and post order traversal, now here in this case A is the root. Then now you divide the whole thing. I can divide the whole thing in 2 parts. 3 node on the left, 2 node on the right. Again how I am getting this? Using this structure. And again using the post order traversal, I can say B is the root. Left, right and then root. So B is the root. B is the root of this. There are 2 children, one is on the left, another one is on the right. So E left, F right. So E is on the left and F is on the right. And GC, C is the root and G is on the right. So now you can again see this thing. If your fundamental idea about this CBT is not clear to you, then you cannot make progress. Because until unless it is clear to you, you will not be able to define the structure. Once the structure is fixed, then you can go ahead and make this division, whatever big structure is. So again in this case, I will go with the statement here in this case is true, that this statement is true that if you have a CBT and only one traversal in order, pre-order or post-order given to you, you can again reconstruct the tree uniquely by using a single traversal. So that is one concept from my end here, that using about traversal, some special case I have discussed, for two-array tree I have discussed, and another concept that I have discussed here is about only single traversal for full binary tree and CBT. So that is the first part of this session. The second question that I am going to take here is this one. The concept of counting of heaps here. Heap structure. And if possible, I will take the another concept, but since we have a time, here it says that consider the following tree. Okay, this is the question. Consider the following tree with 13 nodes and a structure is given to you. What is the number of min heap possible with 13 distinct keys? If the number of min heap possible with 13 distinct keys is x into 10 to the power 6. Okay, the number of distinct min heap possible with 13 node. Why 13 node? Because here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and 13. 13, this is the structure is given to you, and it is saying that there are 13 distinct keys are given to you. 13 distinct keys are given to you. keys are given to you. So how many min heap possible is x into 10 to the power 6. What is the correct value of x up to 2 decimal place? Counting of heaps. Now this question you may say that okay, this structure is not a CBT, but that much creativity we can take for a given question, right? That much flexibility, that much flexibility you must give for sake of creation of question in this case. So 13 distinct keys, and this is the structure that is given to you, and we need to create a min heap, and we need to count how many min heaps are possible in this cases. Great. So now here which one will be the, we will solve this question in parts, and I'll see that whether we have this. Okay. So here if it is a min heap, so among these 13 distinct keys, the root will be the minimum one. Root is minimum. Root is the minimum element. It is a unique element. I cannot say because I have used the word distinct in this cases. So root is minimum, so that will become 1. Then I have 3 structured. One structure, second structure, and third structure. 3 different structures are present in this case. How many keys are remaining? So the number of keys remaining in this case is 12 keys are remaining. Among them, this 12 keys you will distribute here in 3, 6, and 3. 12 keys will be distributed in the case here as 3, 6, and 3. How many ways I can select the 3 keys here? Among them 12, anything can be here, but I need to select only 3 keys. So now this becomes a selection problem, that how many ways I can select 3 keys out of the 12 keys. Suppose 1, 2, 3, 4, 5, 16 and up to 13, these nodes are there, 1 becomes a heap. Rest is 12 keys are there, that is 2 to 13. So which 2 key it will be there? So now this is a selection problem, and I can go for first subtree. I can select this value in 12C3 ways. 12C3. Among these 12 keys, we can select the 3 keys in how many ways? 12C3 ways. Now, what about this 3 key? So suppose I am selecting here as an example that I am selecting here, 1 is gone. So I suppose select 2, 10 and 11. Now I want to construct 3 keys. This is one category. So now here if I want to construct the min heap, this can be constructed in this way: 2, 10 and 11, or it will become 2, 11 and 10. So these 2 keys I can flip it, right? This is also a min heap, this is also a min heap. So 10 and 11 I can exchange. So these 3 key themselves, how many ways I can select? 12C3, and they can arrange themselves in 2 ways. And this is an example, 10 and 11, so 10 on the left, 11 on the right, and 11 on the left, on 10 on the right. So with that, this particular portion, the number of keys are possible is 12C3, and they themselves can arrange themselves in 2 ways. So that is your first part, first subtree. Now we'll come to the second subtree. Second subtree. So what about the second sub? First we will say how many keys are left. So now 1 becomes the root and 3 keys gone over there. Now what? So in this 13, 4 gone. So number of keys left is 9 keys are left here. 9 keys left. Among them 9 keys, how many keys are here? 1, 2, 3, 4, 5, 6. I need to pick again 6 keys. And you know the rule that again there is a selection problem, that how many of them. So remaining 9 I can select again in this cases how many keys? 6 keys. In how many ways? So that is 9, 6, okay, 9C3. That is my second selection for this subtree, 9C6 or 9C3. Both are same, but NCR is equal to NCN minus R, but I will write 96C. So this is the number of selection. Among these 6 keys, one will become the root, minimum, because they are distinct. Again, there is no quotient of repetition. So that it's a simple counting problem actually. So remaining is 5. So one of the key that will be assigned here in this case is how many ways? To 5 ways. So among this 9C3, there are 5 ways by which I can select this particular node. One is the root, 6 minus 1, that is 5. How many remaining? 4. How many I need to select for this subtree? 3. How many keys are there? 6. 1 become the root and 1 become this child. 3. How many ways I can select? So this will become again multiplied by 4C3. That is actually 4. But don't forget that this particular structure can arrange whatever the 3 Qs select from this 4. Just now I mentioned that they can arrange themselves in 2 ways. So 4C3, and here again I will multiply this quantity with this 2. Why 2? Because out of this 4C3 selection, this left and right child can be interchanged. That is allowed in case of the structure of a heap structure. Done. Third subtree. So 1 gone, 6 gone, 6 plus 1 7, and then 3 also, 10 nodes are gone. Ab how many remaining? Only 3. How many you need to select? Only 3. So remaining only one choice, that you cannot make any selection, 3C3. So for third subtree we have only one choice, that is 3C3 in this cases. But I know this is the concept that I am using from the beginning, that these 2 nodes can be arranged themselves, they can interchange the left and right subpart. And if I can interchange the left and right subpart, again here in this case they can arrange in themselves in 2 ways. So now this is the counting here that we have done. The first selection is the minimum, root is the minimum, 12 keys are remaining. The first selection, you can change the order as a practice purpose, you can change the order here. That you can select this 6 first, then this 3, then this 3, 6, 3 and 3, whatever way you can do, answer will not change. Now, so out of 12, 3 selection, 12C3, what is this extra 2? This extra 2 is for this, that they can arrange themselves in 2 ways. How many remaining? 9. How many selection? 6, 9C6, okay, 9C6. Among them, choices, 1 become the root, remaining is 5. Number of selection for this, 5 ways, so 5. Remaining is 4. How many nodes are there? 3. 4C3, changing order, you can do it. 4C3, what is this? 4C3 ways, but this can be arranged in 2 ways. Then how many left? 1. Selection is also 1, 1C1, which is equal to 1, I have not written. Last one is 3C3 multiplied by 2. So the total number of keys here in this case will become this. 12C3 which is 12 into 11 into 10 divided by 3 into 2 into 1 multiplied by, because for each of this there are choices, so they will not independent, they will be multiplied. 9C3, so again they will be multiplied by 9 into 8 into 7, and 9C6 is also 9C3, so they will be multiplied by 3, then 2 into 1, then 5, then 4, then 2, and then multiplied here in this case is then 2, and then one more time 2. Okay, this is the total number of selection here in this case. Okay, so that is the answer for this, and if you just go ahead and solve this, this will become, here in this case is 2. This 2 will cancel out this 8, which is 4. This 3 will cancel this 9, which is 3. Then 7, and if you multiply this quantity, your answer will come 147. Okay, 147. I have already done this calculation beforehand. 400. And if you convert into the 10 to the power 6 form, because my question says x into 10 to the power 6, it will become 1.4784 into 10 to the power of 6. So 1.4784 is the answer for this question. That is the another concept for counting of number of heaps. So I am able to cover 2 concepts here in this cases. First concept is for the concept of post order and pre-order. 3 cases I have told you, and that took maximum of my time because that was a bit lengthy concept. And the second concept is actually I consider it as one of the very good question, that you count the number of heaps possible for these 13 distinct keys for this given structure. So that is the second question, and I am getting this value 1.47. You can say the answer between any value between 1, like in GATE examination we get range. So 1.47 to 1.48 you can put the answer as. Okay. So I hope here that you enjoyed the session, and the entire session is fruitful to you, and you are able to grasp both the concept of the traversal, and this is a concept of counting the number of heaps that you can apply to any other different problems. I hope both of this concept is clear to you. I wish very best of luck for all the aspirant for GATE 2023 and 24. Thank you very much. Good night.
Thank you. My name is Kuldeep. I have done my BTech from Ambedkar Institute of Technology, which is situated in Delhi, and I have secured All India Rank 1 in ESE 2021 from E&T branch. I took ACE Postal Course, Mains Test Series and Interview Guidance Program in ESE 2020 and ESE 2021.
Hello everyone, my name is Karthikeya Kaushik and I have secured All India Rank 1 in UPSC Engineering Services Examination 2021 from Civil Engineering discipline. For prelims preparation, I took online test series from ACE online platform and used to regularly solve their subject-wise test and full-length test. Then for mains preparation, I solved question banks which were given to me as a part of mains postal program from ACE Online. And then last but not the least, for interview preparation, I followed the interview guidance material which was given to me as a part of ACE Online's interview guidance program.
I am Vinit Kumar. I have secured All India Rank 1 in Mechanical Engineering in ESE 2021. I have been associated with ACE Engineering. I have taken various programs like Life's main classes, Postal Study course, test series and interview guidance program. So would like to thank all the faculties of ACE. It has helped me in building my concepts and having my fundamentals cleared. I would also like to highlight that in test series, I have given various mock tests which have helped me in the time of real exam, and in interview guidance program, building confidence in front of interview panel. It has helped me in my success.
Myself, Abhishek Sharma. I have scored All India Rank 1 in UPSC Engineering Services Examination 2021 in Electrical Engineering discipline. Now, I divide my preparation strategy into 3 basic things. The first thing is that you have to complete your syllabus from a basic standard source. The second thing is that you have to attempt previous year question. The third thing aspirant has to do is to solve as many test series as possible. I made 2 to 3 pages short notes of each and every subject. Now 2 to 3 pages short notes help in quick revision. If you keep working hard, you will definitely get success in this examination. This is what I followed, and I wish all the best for all the future aspirants. Thank you. Thank you.
My name is Kuldeep. I have done my BTech from Ambedkar Institute of Technology, which is situated in Delhi, and I have secured All India Rank 1 in ESE 2021 from E&T branch. I took ACE Postal Course, Mains Test Series and Interview Guidance Program in ESE 2020 and ESE 2021.